Every Vibe-coded app, including yours, has these two bugs, and AI put them in there. A while back, I made the case that developers are not being replaced, but the job is changing. You don't write code anymore. AI does. So now your job is to understand it and to review it. But you cannot review what you don't understand. And here is the catch. If you do not have a word for it, you cannot ask the AI to fix it. You cannot even see the bug. You can outsource your thinking to AI, but not your understanding. So today, we learn to identify these two bugs, you understand why they happen, and we learn to prevent them. Let's start with the first one, a race condition. Here's some code, a simple function. A user wants to buy a ticket. We read how many tickets are left. If we have at least one, we subtract one, and we create the order. This is code that you and I can write, and that AI writes all the time. It looks perfectly fine, but it's broken, and you won't catch it in your laptop. Imagine you have one ticket left, just one, and two users want it, Alice and Bob. Alice clicks buy first. Alice's code reads the stock. Stock is 1. Between reading the stock and subtracting 1, there is a gap, sometimes 10 milliseconds, sometimes longer, long enough for Bob's code to start. Bob's code also reads the stock. Stock still 1, because Alice hasn't subtracted anything yet. Now both Bob and Alice see stock equals 1. Alice subtracts 1 and creates her order. Bob subtracts 1 too, and he also creates his order. You just sold the same ticket to two different people. Stock is now 0, but you have two orders for one ticket. And that is a race condition. Two pieces of code racing each other for the same data. Both reading at the same time and both writing at the same time. Neither one knows the other one exists. And here's the part that hurts. This bug never shows up in your computer because in your computer you are one user. Clicking one button in one tab, you will never reproduce this until you ship to real users and two of them click buy at the same time. And now you have a problem. There is even another bug in there, a partial write. Look at these two lines. What if the first one succeeds, but the second one fails? The database connection drops, the server dies, anything. The stock is now one less, but there is no order to show for it. A ticket just disappeared. Nobody bought it. That is a partial write. Half of the operation succeeded, half failed. So let's fix this. We have two bugs, a race condition and a partial write. There are three concepts. Each fixes parts of this. The first word, an atomic operation. Look at this carefully. Notice we don't read the stock anymore. In the broken version, we did three things. We read the stock, we checked it in Python, and we wrote it back. 3 steps, 2 trips to the database. The gap is where Bob slipped in. In this version, we do one thing. We send one line to the database, subtract 1 from stock, but only if stock is greater than 0. The database reads, checks, and subtracts, all in one step. And the database can only do one of these at a time, on the same row. Alex clicks buy, her update runs first, stock goes to 0. Bob clicks buy, his update runs next, stock is 0, the where fails, and nothing happens. Alice gets the ticket, Bob doesn't. That fixes the race condition. But notice something, we still have the second bug. What if this line fails? Stock is already decremented, the update went through, but no order exists, a partial write. The atomic operation does not fix that. For that, we need a second word, a database transaction. A transaction is a wrapper. You put multiple operations inside of it, and the database makes sure that either all of them succeed together or none of them happen. We wrap our operation in a transaction. Now, if create order fails, the transaction rolls back. Rolling back means the database undoes every change we made inside of it. The stock goes back to 1, like nothing ever happened. That is a database transaction. All or nothing. Now we have a fix for both bugs, but there is one more situation. Sometimes you cannot collapse everything into one update. Sometimes you need to read the stock, reserve it, apply a discount, and then update. For that, you need a third word, a row lock. A row lock is a tool that you use inside of a transaction. It tells the database, hold this row, and nobody else can touch it until after I'm done. The transaction is what we just learned. The new part is for update. Thanks to for update, when Alice runs this, the database locks her ticket row. While the discount is applied, the row stays locked. If Bob tries to read the same row, the database makes him wait. He cannot read, he cannot write until Alice is done. Then Bob gets to read, stock is 0, and he does nothing. No race and no partial write. 3 words. Atomic operations fixes the race when one statement is enough. A transaction fixes the partial write, and a row lock fixes the race when you have many statements. The exact code varies by language and library, but the concepts do not. Now you can ask AI for any of them. 3 concepts in your vocabulary. And look at our fixed code. It is safe from races, it is safe from partial writes, but it still has one more bug. This code has no idempotency. Imagine, Alice clicks buy. The function starts running, but the network is slow. Her browser keeps spinning. She thinks the click failed, so she clicks buy again. Again, now the browser sends two requests to your server. Both call by ticket. Both run all the way through. Both create an order. Alice only wanted one ticket, but she got charged twice. She has two tickets that she never asked for. This is what no idempotency looks like. Idempotency means that you can run something once or you can run something 50 times. The result is the same. Like the elevator button. Push it once and the elevator comes. Push it 50 times, the elevator still comes. One. Our buy ticket is not like that. A duplicate request, a duplicate purchase. And it's not just impatient users. A phone loses connection, the app retries a failed request, or a payment platform retries a webhook. The same intent reaches the server multiple times and you accept it multiple times. And now you have a problem. So, how do we fix this? We need to give the function a memory, a way to recognize a duplicated request. The pattern is called idempotency key. The idea is simple. Every time the user starts a purchase, your frontend creates a unique ID, a random string, and it sends that ID with the request. If the request fails and the app retries, it sends the same ID. If the user double-clicks, the browser sends the same ID again. Same intent, same ID. And your server uses that ID as a memory. The first time the ID arrives, it runs the function, it saves the result with the ID, and if the same ID arrives again, it returns the saved result without running the function. The function now takes an idempotency key. First thing we do, we check if we have seen this key before. If we have, return the cached result. We do not run the function again. If we have not seen the key, we run the function as before. But at the end, we save the result with the key. So the next time the same key arrives, we have a memory. Now imagine Alice double-clicking again. First, sends an idempotency key ABC123. Server runs the function, creates the order, saves the result with key ABC123. Second click, same key ABC123 because it is the same purchase. Server checks, sees ABC123 in memory, returns the saved result without running. One purchase, one ticket, no duplicate. The function is now idempotent. You can call it once, you can call it 50 times with the same key, and the result is the same. This pattern is so important. If you have ever made a payment online, there was an idempotency key in that request. If you have ever sent a message in a chat app, there was one too. You did not see them, but they were there. Basically, you want to make your functions idempotent when running them twice would create a problem. Creating an order, sending a message, or charging a card. Anything that should happen only once, no matter how many times the request arrives. This was Concepts for Vibe Coders episode 1. If you liked it, tell me in the comments. There are so many concepts AI won't explain to you. Mutex, hash map, database index, cached invalidation. If you want Concepts for Vibe Coders to be a series, let me know. 오늘도 감사하고 사랑합니다. See you on the next one. 다음에 봐요. Bye bye.